Yeah, welcome back to the second part of my sessions today. I'm Anna Wunderlich, and I'm one of the PhD students here at the Berlin MoBI Brain Body Imaging Lab. And we are now past the ICA session that was quite long, and we'll still work with the independent component properties that we just discussed and proceed with extracting some events that can help to compute event-related potentials, for example, or event-related spectral perturbation. So this is what we're going to do now. And why are we doing this? Because one person's data is another person's noise. That's the original one. But I would rather say like one person's noise is another person's data. So because we can kind of make sense out of things that we record by accident, or even though we want to record only brain activity, we do record, as we have seen, a lot of other activity sources. So we do have eye movement as well as muscle activity and also body motion that are functional and that are task related, and they can be like very informative regarding to cognition. So if we just have EEG recordings in a mobile setup, for example, there is the advantage that participants have to wear less hardware, and also we do have to have like less calibration phases, or we just need less equipment, and this way we can just like passively record the EEG activity and do not have to interrupt the task, like by using a questionnaire or by having to press a button, for example, or whatever. And so events extracted from the EEG activity are just there. There's nothing what has to be added or to interrupt the task. So another advantage is that we are independent of tracking spaces. So we can actually move outside of the lab, for example, and we are not we do not need anything else that captures like the movements. We do not need a person that walks alongside and does like some camera recordings or whatever. So this is another advantage, and everything that's recorded by one device, like the EEG cap, it's already synchronized in time. So this is also an issue less to take care about. But of course, there are quite some disadvantages as well, because the events that we're gonna look at in this session, they're less precise. So if you do extract blinks or saccades or gait-related events from EEG, this is like less precise because it's also like the brain activity drawn to be like distorted by other artifacts or other activity sources. And so if you do have motion capture, or if you do have an eye tracking classes alongside, I always would prefer extracting events from those data. So if you have recorded it, or if you are able to record it alongside without putting a lot of additional effort into it, you just should do it. And something else that makes it more difficult is the more pronounced individual differences in EEG recordings. As we have mentioned shortly only for the independent component analysis, there are various degrees of changes across participants. So I just mentioned that one of the shared data sets is very like there are many of the gate-related independent components, for example, like this is 78, compared to a more clean data set like the 64 that I asked you to look at. So there are different differences in activation. So we also should take care of those individual differences when we extract events. So, and another disadvantage is if you solely have the EEG recording, we do not know what happened in the environment. So for the data set I'm always mentioning, I do not have any capture of what happened around my participants when they were walking outside in Berlin. So there were cars passing by, there were other traffic participants passing by. There was, I guess, a lot of things happening, but I don't know afterwards. Like I just know a little bit about those where I was walking behind, but when the master student was walking behind, I don't know. So this is definitely something you should take care of if you want to, or if you're up to decide whether which source you want to use for your events. But talking about event extraction all the time, this is what we're going to do in the next half an hour. So we select the ICs according to what we learned in the last session. We detect links together. So I walk you through the few script lines that are shared in this data, like in the same file, actually, like you can still have the same file open and just follow the next lines, and then create some events that for EEG lab, and then you can do it yourself. And then we're gonna proceed into epoching, and this does not have to be the next step. And we will also see another version or another possibility tomorrow when we are discussing the Unfold Toolbox. And I'm gonna hint at this at one point as well. But we do the epoching to prepare the session of Marius afterwards for the clustering approach. So for the IC selection in the first point, I just plotted here again, just the activation of the first 20 independent components of this one data set. And we see here, so we have the first independent component showing the blink peaks, and then we have the third one, if you remember, this showing like this rectangular shape for the horizontal eye movement. And for example, 19 in this case does show this like very like regular pattern of a 1 Hertz gate related activity. So those are the 3 patterns that we want to find today. And how this is done here, you can see this in the script. So we have some like EEG plotting. This is actually preparing the plot here. So this is just the EEG lab function for plotting the ICA activation. And then we have the few props function that we have already used also for the IC interpretation session. And so this is for just to double check if like all the properties are actually aligned with that, what we want to see, or like which with the ICs that we want to choose for the event extraction. So basically what I did was choosing them manually. So, but in preparation of this workshop, I was also thinking how this can be done like automatically. So you can find this in the script file for the eye movement. So I just used the IC label classification because it's pretty good for eye movement, and eye movements are not that different in MoBI setups than compared to stationary setups. So I just defined that the first, like the most contributing eye component is the blink, and the second eye component that contributes a lot to the data is the horizontal eye movement. So those lines are also in the file that I shared, so you can have a look at this. In the next step, when you have defined the independent components, it does make sense to use for the blink detection the absolute value. So this is what I plotted here at the right side. So this is like the actual activation. So this fluctuates around 0, and the blink peaks are on top. And sometimes the IC solution flips around the activity. So this is not like this is randomly chosen. So sometimes participants do have a flipped version of the blinks, and to have like the same approach for all, you can just choose the absolute value. So you still have like clear peaks that you can detect in the next step. And after having the absolute values, we're gonna look at the, I thought I have another slide for that, but no, I don't. So there is this, I used the smooth data method with the moving median for smoothing the data set a little bit. And because like using the median for smoothing in comparison to the moving average, this keeps like the sharpness of the peaks. So the how the peaks like rise and fall, this is remaining, just like the fluctuations in between are smoothed out a little bit. So this I found was more helpful than having a moving average and just smoothing everything out. You can also use this code line and check it out and compare it, and then learn what is best with your data in this case. So, and for the blink detection itself, I simply used the find peaks function. There I also, plotted the reference here from MATLAB. I actually don't know who it actually developed. So, but yeah, it's a nice function. So you hand over to this function different parameters of your peak that you want to detect. And for this, there is this figure. So there is a definition of peak prominence. This is above like the activation, in our case, like the data that is before the onset of the peak. So if that's higher, peak prominence is smaller. For example, in this case, then here, even though like the absolute amplitude or magnitude above 0 is pretty similar, like the prominence is very different. And also you define like a width of the expected peaks that you want to detect. And this is like really helpful for using it for blink detection, because in the eye movement related activity, you have a lot of peaks, but just some of them have like this clear shape of the blink. And here, using those properties, you can actually like get to a very good representation of a blink peak that you want to detect. For example, if that would be like eye blinks, and you define those values or something alike, like this would be detected as peak in this, but those guys not. So this is really helpful. If there's a mixture of activity sources contributing to the independent component, you still can just detect the peaks of this, like of the blink. And what you can also see here, there is also minimal peak distance between peaks. So this is also nice for detecting physiological measures, because you can actually read about like blinks and how they happen and what's the usual timing between blinks and stuff like that. So I actually also did that for this cat detection, that I checked out how this physiologically works and how how far in timing they should be or not. So this is pretty nice. So you can define that on a like theoretical basis, how the peaks that you want to detect are defined. And here in the peak prominence, as well as in the threshold, I use individual measures. So this is like percentiles of the activation of this independent component. So this takes care of the point that I mentioned, that we do have this huge individual differences within independent component analysis solutions. So having a relative value here helps a lot. To have a one for all approach, still accounting for the individual differences. And saying that, I'm gonna share, just go on to the next slide, where plotted the histogram of the IC activations of this blink component. And as it is the absolute values, it starts at 0. Otherwise, it would look different. So, so you usually, if you don't use the absolute values, you would have like a more Gaussian, not that high peak, and then you would have like a kind of a plateau or even a secondary peak here, and so because of the blinks. So this is like also a pattern that's like very close to the, or yeah, that I found a lot for blink related independent components, so that you have this double peak. But if you use the absolute values, you have more or less like half of the Gaussian curve. And then you see here the 85 percentile, the 90, 95, and 98 percentile. And so what else you can do is just also detecting the knee point, for example, to define which percentile you want to use, like to actually individualize it even more. And this can also improve. I'm not stating that I have the perfect blink detection, but this one works. So, but I just wanted to show you where like the thresholds are set for this one here. So it's the 85, it's the first for the threshold. So this is an absolute value that has to be passed. So that's a little lower than the prominence that has to be above the previous activation. Okay. And then the next step, we can use those blink like peak. Well, let's go back. So this function gives you back the blink peaks and the blink locations. So you can use the blink locations. In this case, like in general, it's like peak locations, of course, but in this case, it's the blink. And those blink locations you can use to define the event latencies and then create the EEG events, how they are meant to be in an EEG struct. So yeah, also something that you can afterwards see, like you can simply plot again the IC activations, and then your EEG, new EEG events should be in there. And what you can see here is that there are like actually the first sample that is above and marks the event. So maybe there could be even more improvement for this blink detection to actually have the peak, like the, but this may be due to the smoothing that it's actually detecting the first sample. And in my case, that did not matter because I wanted to have like it similar for all peaks. So if I have blink related potentials later and the peak is always detected the same way, this is not an issue. But if you're like really into analyzing the blink itself, yeah, things can be improved as well. And just another example, I will not go into much detail about the saccade detection, but it's also part of the script. And but if you plot it later, if it works out well, it looks like that. So you actually have the blinks well detected, as well as here's no blink, but here's something going on, and you have this peak is detected as well as those. And some misses. So, and this accounts for the saccade because the saccade detection works with the square root of the vertical and the horizontal eye movement. And so this is like an ER-EOG approach for detecting saccades that I found. So this is something that can be useful. It's not, I did not get it as perfect, as good in quality for detecting saccades as I did get it for the blinks. So blinks are easy to detect and saccades are more difficult. So yeah, it's just because of how the IC activations add on. So because there are always like some remaining other activations, you may have more or less losses or misses or false alarms when detecting your events. Right. So we are already getting to the do-it-yourself. And this slide is a little busy, and because I added all the code lines as well. And so again, we do have like, it's just the like the steps I just explained. So you can use the gate-related component. It's for VP64, it's the IC19 I would recommend. And then you can go through that. So, but I guess it's better to do this as a homework, and a slide's gonna be uploaded, so you can do this afterwards. And I just want to show you something else, why I am pretty convenient that this is gate related. So there is like some alignment with the motion capture, and this is not scaled. So these are two motion capture streams of the right and the left foot, and as well as the sum of both. And the IC activation is just aligning with the rhythm of the walking. And but this is actually already a spoiler alert for the session of Urosh and Betty tomorrow morning. And another spoiler alert actually for the Unfold toolbox and what we can do with our events that we just extracted. We can unfold the EEG activity for like different kinds of blinks, task related. They're separated here, so this is a different data set. That's the other one. And yeah, what you can see here is like the step related activity that we got in this data set, because I think this is because like blinks may actually line up with some steps, and was more pronounced for some participants than others. So this just shows how those events can be used as well for the unfolding. But and then after like unfolding that, you get rid of all the gate related activity and have more smooth blink related potentials, for example, like that. Now we have 5 minutes left for the take home message as well as the epoching. So yeah, so what we learned in both sessions is basically EEG records more than brain activity. Well, that's no surprise. You all knew that, I guess, but we can utilize that, and it's not a bug, it's a feature that we can actually use to have nice approaches for putting together the MoBI, like the movement as well as the brain activity. And if we want to prepare just in short the IC clustering session, we need to epoch the data. So this is related to events as well. So we're just following the path down here today, and we can use the events we extracted from the EEG, from the EEG activations. But for now, we go back to the actual stimuli that were presented in the data. So we can use these code lines that are also in the file that I share with you. We did do for the epoching for the ERPs this filtering, and then we just cut the epochs around those events. I did it like this because all the event information did contain like the current timing, I think, or a lot of other information. So I just searched for the first characters in the event, and then collected all those in an epoch events variable that I then used to epoch using the pop epoch function from -600 milliseconds to 1400 milliseconds. So depending on your variables and features that you want to extract from your epochs, you should vary that and prolong the pre-stimuli time for especially spectral analysis, for example. And then you need to define a baseline, and that is like subtracted from each individual epoch, and to align them in the stimuli onset. Good. And I think I'm gonna skip the epoch cleaning. So yeah, I think it's nice, and you can look into it, and everything of the epoch cleaning is also saved into eeg.etc. And yeah, and I can hand over to the IC clustering.